Okay, let me. Okay, so welcome everyone for our EC colloquium talk. Today we have a very distinguished speaker, Dr. Michael P. Frank. He is from Sandia National Laboratory, Albuquerque, New Mexico. And so I have been interacting with Dr. Frank since long time when I was a student actually, and it was one of my time that I was interested in working with my PhD with him actually. So it's very pleasure to have him here. And let me introduce a brief biography of Dr. Frank. Dr. Frank received his BSc in Symbolic Systems from Stanford University in 1991 and his MSc and PhD degree in Electrical and Computer Engineering, Computer Science from MIT in 1994 and
94 and 99.
Yes, 1994, 99 respectively. And while at MIT, he helped design his first adiabatic and reversible programmable CPU CMOS processor that was ever built. After graduation, he continued his research in reversible computing with adiabatic CMOS at the University of Florida and Florida State University. And currently, he is working at Sandia National Lab from 2015. For the last several years, he has also helped to edit the Beyond CMOS chapter of the IEEE International Roadmap of Device and System. And it is my pleasure to say that he's one of the pioneers in this area. So it is one of the greatest pleasure to have him here. So with that, we'll let Dr. Frank to continue his talk.
Thanks, Himanshu. So I guess I'll share my screen and then hit the button to start. Can you all see that?
Yes.
Great. So the title of my talk is Perfectly Adiabatic CMOS Logic. And this is an area that, has been kind of explored for a long time, but it has not so far been the focus of most adiabatic circuits work. But I argue this is something that's going to be increasingly necessary going forwards. So just the structure of the talk, I'll talk a little bit about the motivation for this work from fundamental physics and a brief history of work that's been done in this area. And then I'll talk a little bit about what are the requirements for what I call perfectly adiabatic CMOS, by which I mean a CMOS style that is both fully adiabatic and fully static. So I'll explain why that is beneficial for low power design. And then we'll go into some detail on the new logic family we invented last year, which I call S2LAL, for static two-level adiabatic logic, and show a little about its structure and timing. And I have some news that wasn't reported by me previously, which is that there is now a new variant of S2LAL that is half of the complexity of S2LAL, roughly, which was developed by Eric de Benedictis. Based on S2LAL, he found some ways to further optimize it. So that only helps the practicality of these techniques. And then I'll just wrap up. Okay, so we'll start with motivation and history. So of course, the motivation for trying to do fully adiabatic circuits comes from Landauer's principle. And I have a little sketch here showing the basic argument for Landauer's principle, which is that if you have correlated systems in a computer, such as in this example, you've just got two single bits that are correlated, they have the same logic value. And then you try erasing one of those bits in isolation, that corresponds to sort of merging these two computational states. And then the information can't be physically lost. It has to go into the microstate of the system, which then in general gets thermalized. And when this happens, you have an entropy increase of 1 bit's worth of entropy per each bit of correlated information that's erased. And so that's the key motivation for why you want to avoid erasing information in isolation. All right, so that leads to the need for reversible computing, in which we try to avoid erasing information. And in principle, if you're computing in a way that is logically reversible, then you can also approach thermodynamic reversibility. So you can reduce energy dissipation to arbitrarily low levels. And for the most part, people doing adiabatic circuits did not historically try to push things that far, but it's going to be increasingly necessary to do that as we want to push the limits of energy efficiency of computing. Just a few key historical developments. Bennett first showed in 1973 that reversible computing was logically coherent, that you could compute in a way that just leaves around your desired output and a copy of the input and decomputes any temporary garbage information that you have to leave around. And the earliest engineering implementation was actually one by Likarev, who was at Moscow State University at the time, and he's since moved to State University of New York, and he's now retired. But in the 90s, 80s and 90s was early research towards adiabatic circuits, and a key milestone was this 1993 paper by Eunice and Knight, which I'll show a little more about briefly, which was the first fully adiabatic logic style for general sequential pipeline logic in CMOS. And then in the late 90s at MIT, my fellow students and I designed several fully reversible processors. TIC here was not adiabatic, it was just a conventional implementation of a reversible instruction set, 8-bit. And then Flat Top was fully adiabatic, sort of a gate array style processor. And then Pendulum was a MIPS-like processor with, I think, like 12 bits or 16 bits, can't remember now, but it was MIPS-like. And I think the time is ripe at the moment for a resurgence of reversible computing research, because we are coming up on the limits of CMOS technology. Like the roadmap only goes out about another 10 years or so, and it's going to be really hard to push beyond that using non-reversible technology. So I think techniques like adiabatic switching, energy recovery, and reversible computing are going to become increasingly important moving forwards, even for general computing, let alone security applications. And there's sort of a key economic argument for why we have to move to reversible computing eventually, which is that if we don't, there's a floor on the amount of energy used per computational operation. And I argue energy always has an economic cost associated with it. If nothing else, there's the opportunity cost represented by the fact that, if you dissipate some energy for computing, you can no longer use it for some other purpose. It's been degraded to waste heat. And I mean, maybe you can reuse some of the waste heat for like heating your building in the winter or something. But, other than that, the energy's gone, right? And so conventional computing is never going to be able to get below this cost floor per operation. And that implies that the cost efficiency for conventional computing is going to reach a ceiling where we can't do any more computational work per, kilowatt hour of energy that's expended and associated cost. Whereas with reversible computing, we don't have that limit. And even though the total cost of computing includes manufacturing costs as well as operating costs, well, the operating costs still set a floor on your total cost, right? So it still implies the cost efficiency of conventional computing can't increase beyond a certain point. And with reversible computing, all we have to do, and I'm kind of underemphasizing it, but we have to keep improving manufacturing costs to keep the total cost being reduced. But in principle, we can do that. And as long as this cost coefficient out front in this term keeps decreasing, even if the time per operation is increasing and maybe even the size of our devices is increasing, as long as the efficiency of the manufacturing technology can keep improving, this whole manufacturing cost term, time amortized manufacturing cost term, can keep declining, and we can keep reducing the total cost per operation as far as we want in principle, and keep improving system level cost efficiency as far as we want. So the argument is that, eventually reversible computers will be far more cost efficient than any physically possible non-reversible computer. And at that point, sort of almost all computing that we do will necessarily be of the reversible flavor. And, this is an evolution that will probably take decades to play out, but we're starting to see some commercial interest in it now. So we may start to see early applications for certain problem domains in the relatively near future. And some of those include the, stealth security applications that Himanshu works on, and some of them include things like low power electronics for control of quantum computers and other cryogenic systems. So there's lots of exciting opportunities, I think, to see this stuff start being applied in the not too distant future. Okay, I mentioned I was going to describe the 1993 logic style of unison night in a little more detail. And they called this charge recovery logic, which is kind of a misnomer because, charge is conserved. So any circuit does charge recovery, right? But the point is it's recovering charge at the same voltage level that it came into the circuit at, right? So it's an adiabatic logic style. And this figure from their paper is a little misleading. It makes it look like there's 16 rails here, but that's for two different logic values. So you might think, okay, it's an 8-rail logic, but actually it's not. There's twice as many rails because it has inputs both from the preceding stage and from the next stage. So each signal is really only 4 rails. It's quad rail logic, same as 2-Lao. And in fact, I didn't realize it at first when I invented 2-Lao, but CRL is almost identical to 2-Lao. So you can take this circuit and through just a series of transformations in how it's being represented, it maps almost exactly to 2-Lao. 2-Lao is a adiabatic logic style that I described at University of Florida in my lecture notes in the year 2000. And we've done quite a bit of work on it since then. But 2-Lao essentially ends up only being a slight generalization of CRL. And I won't go through all the details of it because it would take too much time. But then the following year, they invented a somewhat simplified version of this that went from the quad rail style to a single rail logic representation. And they came up with a number of different clocking schemes for making fully pipelined, fully reversible logic out of this. And they even had versions that they called static, although I later discovered there was a bug. They were not actually fully static or fully adiabatic, it turned out. And the problem is easy to fix, but it was there in the early chips we did had that bug in it. So we're not technically fully adiabatic. And you can also see that this clocking scheme is pretty complicated. There's a lot of different clocks, all of these plus inverses, and there's a lot of different time intervals per clock cycle. 24 ticks, in fact, per clock cycle, where a tick is a transition time. So we'd like something that was faster than this, and we'd like it to be fully static and not have quite so many clocks. And so that's what I was trying to do in the current project. So I wanted a new pipeline adiabatic logic family capable of general sequential reversible logic that could achieve fully adiabatic operation. And I'll explain in more detail what that means. And it could achieve fully static operation. So all circuit nodes are connected to some reference at all times. And this helps, this simplifies design, because if it's not fully static, there are parasitic couplings that can disturb voltage levels and lead to problems. I'll talk about that more later. And we want the latency to be minimal. So in other words, each layer of combinational logic depth that you add should only add one adiabatic transition time of latency to the operating cycle, or to the latency of the entire combinational circuit. And we do fine-grained pipelining in these circuits. So even a large combinational block would have a number of pipeline stages in it. So, so you don't actually increase the clock period as you add combinational stages, but you just add more pipeline depth. And we also want maximal throughput. So that translates into a clock period that's as short as possible relative to the transition time. And what we found in this work was that we could achieve all the rest of the goals with a clock period of 8 ticks, but we cannot do it with any less than 8 ticks. And I wouldn't say it's quite been rigorously proved yet. It's not like we formally explored the entire space of circuit styles, but there was no obvious way to improve this technique to be any faster. I'll just put it that way. Okay, so let's talk about the requirements in a little more detail. So for a circuit to qualify as adiabatic, fully adiabatic in my terminology, it has to obey certain rules. You can't have any diodes in the charging path because for fundamental thermodynamic reasons, there's always a voltage drop associated with the forward bias diode that, you cross the diode, you also undergo a decrease in voltage. And so that sets a floor on the energy dissipation for a given amount of charge transfer. And so you have to avoid diodes. And I mentioned this because some of the early quasi-adiabatic logic styles actually used diodes in the charge return path. So we have to avoid that. And then there's also something called dry switching, which is terminology that comes from old electrical logic schemes based on electrostatic relays. And, if you're using actual physical relays that make and break contact, you find that the contacts get corroded if you don't be careful not to have a voltage difference between the two terminals when you make contact, because if there is a voltage difference, there will be a spark. And you also have to make sure that there's no current flowing when you break contact, because if you break contact and there's a current, well, there's always some inductance associated with your current paths. And so if you suddenly stop the flow of current, there will be a voltage buildup that will again cause sparking. And in CMOS, it's slightly more subtle that the reason for not turning off a transistor when there's a voltage drop across it is that as you're turning the transistor off, it doesn't turn off immediately. There's a gradual increase in the effective resistance through the channel as you're switching the gate to the off state. And as that resistance increases, now your voltage drop, your IR voltage drop across that resistance is increasing. And so the current is kind of gradually tapering off, but as it's tapering off, the charge is flowing over a greater voltage drop. So you find you get a spike in energy dissipation if you try to do things that way. So there's this rule: we don't want to turn a transistor off when there's a current through it. And if you carefully go through a lot of adiabatic logic styles in the literature, you find that a lot of them break one or the other of these rules, particularly the no squelches rule, as I call it, where you don't turn off a current flow suddenly. And so you have to actually take some extra care if you want to avoid these events. And it ends up implying that your driving waveforms have to have this quasi-trapezoidal shape. And these flat regions in the waveform are needed because you want the channel of a device, its source and drain terminals, to be quiescent at a stable static voltage level as you are changing the gate of that device, so that you're not turning it on, turning it off, or turning it on at the same time you're trying to push current through it, right? So So you have to have these flat regions. And of course, for adiabatic charge transfer, we want a limited maximum slope for the transitions. It doesn't really matter if the corners are rounded or if the shape of the transition is perfectly straight, as long as it isn't too steep, because any steepness in this transition will lead to a larger value for the integrated power, I squared R power. So, okay. So that's why we want fully adiabatic operation, is, to avoid limits on energy efficiency. Now, why do we also want it to be fully static? Well, the trouble is, if your logic style is not fully static, that means some circuit nodes will be floating dynamically for at least part of the clock cycle. And an example of this is a DRAM cell, where you charge up a storage transistor, and then you disconnect it from the rails and you just leave it floating, and it will gradually leak current away. And that's why you have to refresh a DRAM periodically on like a millisecond time scale. And so this happens generally in logic circuits as well. If you had an isolated logic node, even for part of the clock cycle, there will be some leakage, and that includes subthreshold leakage through the channel, and also gate leakage due to tunneling currents between the circuit node and the gate electrode. So as a result of that leakage, there's a gradual voltage drift in the voltage level on a floating node over the course of a clock cycle. And that can lead to problems, because like when you reconnect that floating node to one of the sources, if its level has drifted, then you'll suddenly get this CV squared magnitude dissipation when you reconnect it. And then even aside from voltage drift, there's also an even more insidious problem of what I call voltage sag, which is that any circuit is going to have some parasitic couplings between your floating nodes and other nearby nodes, such as a nearby clock line, a gate of one of these devices if it's connected to some other logic. And so in general, there will be perturbations to the level of a floating node, even in the absence of leakage, right? And again, if you don't happen to exactly restore these capacitive perturbations to the original level at the time you reconnect this node, you'll again get this CV squared magnitude dissipation. And the voltage here is, the magnitude of the voltage discrepancy from the ideal level, but it still can be a non-trivial amount, right? And, you could imagine engineering the circuit so that all of the capacitive couplings are carefully balanced so that they cancel out exactly. And maybe you could engineer even the voltage drift effect so that there's equal amounts of leakage to different sources. But that's all a very delicate thing. And we don't expect it to be very easy at all to do the physical design of a circuit in such a way as to exactly balance all of these effects. So an alternative to that is to make your logic family fully static. So meaning every node is connected to a reference at all times. And so, there's no net drift because you're always tied by a lower impedance path to a reference source. And so you're always staying close to that reference level. And whoops, jumped ahead too quickly. And similarly, if any capacitive couplings still exist, but they don't affect the voltage level, they represent a flow of path through the capacitive chain, from your power supply to your source, or from whatever node is fluctuating to your sources, right? And there may be some dissipation associated with that, but you don't get this buildup of this, quadratically large energy gap due to those capacitive couplings. So we believe that fully static, fully adiabatic styles can actually get to far lower levels of dissipation in the long run as we continue pushing this technology. So that's the motivation for why fully static adiabatic CMOS. And rules for how to achieve that just include basically that every time each node, it's either connected to a constant voltage source or, to a variable voltage reference, or it can be transitioning between being connected to a constant voltage source or variable voltage source, as long as they're at the same level at the time that you're doing that transition. This is kind of stated in qualitative terms, and basically, the closer you get to achieving this, the lower your limits on energy dissipation can be. And, just as a benchmark, let's say something on the order of tens of kilo ohms would be a typical impedance through several turned on transistors, minimum size transistors, to a reference source. And if it's less than that, that's great. But of course, you want your path through turned off devices to have a much greater impedance or effective resistance to reduce leakage. Okay, so now let's look at S2Lal in more detail. And just to introduce my notations, I'm just going to use two standard voltage levels, and we assume that the logic high level is substantially over the device threshold. And we divide time into ticks, as I mentioned earlier. And there's this formula that goes back to ATHIS, at least from 1994, about the energy dissipation for an adiabatic transition. And you've all probably seen this formula before. This is the transition time. This squiggly thing out front is chi is a shape factor, and it's just to account for any departures of the ramp shape from the ideal shape. And this is a formula that's valid asymptotically as you go to longer ramp times, and there's an interpolation between this and the normal 1/2 CV squared dissipation that you would use for taking it to very short ramp times. But the key thing here is the transition time is larger than the RC delay of the charging path. And then we'll assume our clock period is an integer number of ticks, okay? And we'll just number ticks within a cycle cyclically. So let me talk a little about our quad rail logic representation. And like I said, this goes back to the original CRL style of unison night, essentially. And it's adopted in S2Lal, but I'll show a different style later that improves on this and gets us down to just quad rail. But in S2Lal, we represent a logic signal with a pair of pairs of wires, and each pair of wires is for representing one of the values of that logic signal. An interesting feature of this representation is it makes it very easy to go to in-array logic. So if you wanted to do ternary logic that had 3 different values for the logic symbol, 0, 1, and 2, or -1, 0, and 1, whatever representation you want, you could do that just by having 3 pairs instead of 2 pairs. It's simple to expand the number of possible logic values. And then each logic value is represented when it's present by a pulse on a complementary pair of signals. And the reason we need these complementary pairs of signals is for driving CMOS transmission gates, in which the PFET and the NFET making up the transmission gate need complementary gate voltages. So basically, with these pairs of signals controlling transmission gates, then the transmission gates are either strongly off if we're in this state, or strongly on in this state, or we're transitioning between those two states. But as I mentioned earlier, we take care in these logic styles not to try to push current through a switch as we're turning it on or turning it off. So that's one of the rules here. And I have some symbolic notation for representing these signal pairs, but you don't really need to memorize the notation unless you're going to go through the whole paper in detail. We also have this logic style called 2Lal. This is, again, the same as CRL, essentially. which I'll show this first before I show S2Lal, just because it's a little simpler. So in 2Lal, we have 4 different clock phases, and each clock cycle is 4 ticks long. We have logic signals that go valid and are held valid for just 1 tick, and then go invalid. And when I say valid, I just mean that they contain some logical data. And in the invalid state, they're in this unconditionally inactive state. And it turns out that the structure of a shift register in 2Lal is extremely simple. We have these transmission gates, although actually this icon is representing a parallel pair of 2 transmission gates, because these are all dual rail signals. And so every line here is a pair of complementary signals, not a single signal. But other than that, this is just a transmission gate. And here we have another transmission gate, and notice the mirror image structure between those. This one is used for moving data forwards in the pipeline, and these are used for decomputing data backwards in the pipeline. So to do everything reversibly, you're basically doing a reversible copy of data from this node to this node. And then once it's here, you do a reversible uncopy, where you're decomputing the value of the previous node using the value of the next node. And that's how you can move information down a pipeline reversibly. And in this example, the stages of the pipeline are just buffers, but you can also have more complex logic in the stages. As long as it's invertible logic, you can compute the next stage of, you could have a whole bus, a whole array of parallel logic signals, compute the next value of that bus, and then decompute the previous value of the bus. And we did some simulations last fall that were in the process of fleshing out in more detail, but a preliminary result was that you could get down to an attojoule scale level of dissipation per device per cycle. And that's well beyond the even end of roadmap CMOS. And it's beyond where a number of other quasi-adiabatic logic styles can get. And there have been some papers that do some comparisons of 2Lal and other adiabatic logic styles that show that 2Lal can do about an order of magnitude better than the nearest competitors. And that's in this particular process, which was a 180 nanometer process that we have internally at Sandia. However, the limits on dissipation can go even lower if you have a process that is specially designed for low leakage. So anyway, we actually taped out a test chip for this, and it's in process now, and we hope to get that back sometime this year and actually do some testing on it. So now let's look at the circuit elements of S2Lal in more detail. So in S2Lal, it's not enough just to have these transmission gates, because the problem is with just the transmission gate, you're sort of dynamically latching the output node when the transmission gate turns off. So instead, we also have a separate MOSFET here that is just used to clamp the output to a constant voltage rail. And it's going to do this in the part of the clock cycle during which it's not connected to the variable voltage source, or on clock cycles where it's not connected. So the point is that the output is always going to be connected either to the constant rail or to the variable source. So here's an icon just for this buffered for this static buffer. And then you can make a latched version of it where you add a transmission gate to the output. And we'll see this is used for handing off control between forwards and reverse gates. So, just looking at this structure, it's not necessarily going to be fully static or fully adiabatic, but when you integrate this into larger pipelines that are carefully designed, then you can make everything fully static and fully adiabatic. So let's see how that works just at a high level. Here's the pipeline structure. We have these latched static adiabatic buffers. And, again, we have forward and reverse pairs. And we have to change the timing sequence. So in S2LAL, for fully static operation, we have to lengthen the clock period to 8 ticks. And now each clock signal is in the active state for 3 out of the 8 ticks, inactive for 3 out of 8, and transitioning for the other 2. And the logic signals are valid for 5 out of the 8 ticks and invalid for just 1 out of the 8 ticks and transitioning in between. And the reason why these have to be wide is because for fully static operation, we have to make sure that any given logic signal, like take S1 here, is being actively driven or it's connected to a source through either the forward buffer or the reverse buffer at all times. And there is a period when it's transitioning from being driven by the forward buffer and the reverse buffer. So essentially it has to stay active long enough. It has to stay valid long enough that you can propagate its value through to the next node, then prepare to drive it from the succeeding reverse buffer. Then you can hand off control from this forward buffer to the reverse buffer. And then you can roll back the value of the preceding node and then undrive. You can roll back its influence on S1 from the preceding node, and then you can undrive it through the reverse gate. So if you just count the number of steps that have to be done in sequence in that whole process, you find it's 5 steps. And that's why every signal here has to be active for at least 5 ticks. But if it is, everything works out. And after you've decomputed, let's say you've moved the value of S1 to S2, and then you decompute the value of S1, then you hand off control back from this reverse buffer to the forwards buffer. And now you're ready to begin loading in a new bit value. So that's the 1 tick when it's inactive is when you're doing that handoff to prepare for a new computation cycle. So, this is all very carefully worked out, and I believe you can convince yourself if you go through the details of this that you can't make the clock cycle any shorter without breaking the either the fully static property or the fully adiabatic property of this logic style. But if you're willing to put up with an 8-tick clock cycle, then now you can do any reversible computation in a fully pipelined way in this logic family. Here's what the actual Boolean gates look like in this family. Notice they're more complex than conventional gates, and more complex than things like SCRL gates, which was the single rail logic family. But again, they're fully static, and we only need 2 voltage levels, which is one of the other advantages of the 2LAL and S2LAL families. And you may wonder why there are so many transistors here. It's just because every single node of the circuit has to be connected to a source at all times. So for example, you can think of this as a pull-up path, where A and B come in, and if they're both true, then this path is connected. Well, there's a node in between A and B, and so you have to worry about that one. And this extra transistor here is used to make sure that this node is always, if A is turned off and B is turned off, for example, we don't want this node to be left floating, because then its voltage level can drift or it can sag, and then as soon as we reconnect it, you get a non-adiabatic event. So instead, we have this transistor here, which is arranged so that if A is off, so it's not connected to the variable source, then we end up being connected through this path to the constant source. And so you can go through all the cases yourself and verify that no matter what the values of the logic inputs are, that every node in the circuits is connected to one source or the other at all times. And the circuits are in complementary pairs, right? Because that's our representation. And here's an OR gate, which is similar to the AND. And kind of the reason why we need a quad rail style and not just dual rail in the original 2-lao is because notice these are non-inverting gates. And so if you want inverting logic values, you have to do that some other way. And one way is just by having the logical complement of every signal explicitly present. And then you can do a NAND using De Morgan's law. You can turn that into an OR of logical complemented signals. And similarly, NOR can be done in terms of AND. NOT is just a buffered version of the complemented signal, and so on. So that all works, and you can do universal logic with it, but it's annoying that it has to be quad rail. So Eric de Benedictis figured out a way to simplify this to a dual rail version, and I'll show just a brief slide on that in a minute. One more important issue is the question of how you do energy recovery in adiabatic circuits. And, there's been some work on power supply designs for adiabatic circuits, but most of the designs are not trying to really push the limits of the efficiency that's possible. And we're trying to really push the limits of the energy recovery efficiency. And our approach for doing that is to design high quality, fully reactive linear circuits with, high, precise tolerance components. And the idea here is that you can represent any periodic waveform as a superposition of its Fourier components. And the components are just harmonics of the fundamental frequency. And what we do is we have a coupled set of tank circuits here that are, they're coupled together by sharing a common current path through these transformers, and which keeps them in phase with each other. And each of these naturally is oscillating at a different harmonic of the fundamental frequency. And we also have a turn ratio here in these transformers, which is designed to ensure that the relative amplitude of the effect that each of these has on our output signal here is properly proportioned. And so the net effect is you have a weighted sum of Fourier components that these circuits naturally resonate at, so that they naturally tend to settle on these trapezoidal looking waveforms. And of course, no circuit is perfectly efficient, right? So there's going to be some losses, and you make up for those losses with an oscillator driver circuit. But it's only got dissipation of an order that's needed to make up for the dissipation in the resonant circuit. So I would say there are some engineering challenges to making this practical, because this is just sort of an abstract circuit concept. We have to actually implement this out of real components, and we have to do a careful job of coupling those to an actual adiabatic logic chip in a way that reduces the parasitics and gets as close as we can to a high Q solution. But if you simulate these circuits in isolation, it looks like the Q is several thousand. I expect that once this is fully integrated with an adiabatic logic chip that you're driving, that's going to decrease somewhat because of various non-idealities. But I feel like there's a good opportunity here to do some more detailed design studies for resonators like this, and show that they can really lead to great improvements in energy efficiency compared to anything else that's out there today. So anyway, we filed a provisional patent application, and the full details of this are not public yet, but they're available under NDA. So if there's commercial partners or academic partners that want to collaborate with us on this, we can definitely work with them. Just very quickly, this is Eric de Benedictus's simplified version of S2Lal. So essentially, he's getting rid of the need to have both the logical and electrical complements of a given signal. So he just has this a pulsed version of the signal and a version that's quiescent, and it's just the choice of which one is pulsed reflects the logic value. And the waveforms are basically the same as S2Lal, except there's only one signal in each pair instead of two. And the design of the gates is similar to S2Lal. So the static buffer is similar, but there's an extra transistor here, which is controlled by a clamp signal that ends up getting derived directly from the clocks. So it's just, you can think of it as another clock waveform that doesn't need an independent source, but can be computed by clock gating on chip. And similarly, the logic style, it supports both non-inverting and inverting gates. And here's an example of a NAND. And again, he's using these special clamp signals that have a different waveform than normal clocks, but still periodic. And so I'm not going to go through all the details of all this, in part because I haven't had time personally to digest all of the details myself. But here's the paper, and I would encourage you, if you're interested, to look at that, as well as the rest of this was all presented in a paper at ICRC last fall, and I've been showing the title of that paper on all my title slides. So just to wrap up, there's lots of things that we can do with this going forwards. We can continue to do more simulation studies. And in fact, we're not quite ready to present it yet, but we have some very nice simulation results showing that if you plot the dissipation versus frequency for S2Lal, you get this very beautiful clean curve that's very close to the theoretical ideal, where the slope of dissipation versus frequency, it's a straight line with a slope of 1 on a log-log chart, showing that dissipation per cycle is exactly scaling with frequency at high frequencies. And then it hits a minimum where the dissipation from leakage and from adiabatic switching are equal at that minimum. And then at low frequencies, the dissipation goes up linearly with the clock period because those are all leakage losses at the low frequencies, or dominated by leakage losses. And so that all looks very beautiful. It's logically correct and stable at any frequency because drift is not a factor and sag is not a factor. Because otherwise at high frequencies, certainly, AC coupling through capacitors starts to be a big problem. We'd like to fabricate those chips and do some measurements. And then one very interesting thing is, because S2Lal is so stable, it's very easy to design with. Like basically, if you just follow the design rules and the clock phases and so forth, any CMOS designer could work with this logic style. And you'd still have to do full custom design for now because the tools aren't going to support automated synthesis yet, but you could at least do an open source library of reference cells and example designs for simple IP for static adiabatic CMOS. You could even design a adiabatic FPGA using these kinds of cells, and thereby make adiabatic circuits much more accessible to people in the academic community, especially who maybe don't want to have to worry about all of the careful kinds of balancing of parasitics and so on that you would have to worry about to really optimize adiabatic circuit designs if they were not fully static. So we think this will help adiabatic circuits to gain more traction in the tech community in general. We also have an interest in exploring the use of these circuits at cryogenic temperatures. There's some big advantages there. One of them is that the subthreshold slope gets much steeper at low temperatures, which means you can do either one or both of lowering the off-state current, so to reduce the leakage losses, or lowering the operating voltage, right? Because now that your subthreshold slope is steeper, that means your thresholds can also be smaller. Your logic swing voltages can be smaller. And also there's interesting opportunities to have re-optimize the transistor structure so you can reduce gate leakage along with the subthreshold leakage. Also at low temperatures, you can somewhat decouple the whole power supply problem. So if your power supply is at room temperature and your actual logic is at the low temperature, you may not care about the dissipation in your power supply and might not even need a resonator because you're just trying to reduce the dissipation down in the low temperature environment. And even if you do want the whole system to be cryogenic, or you want a tighter coupling between your supply and your logic, you could use superconducting resonators at low temperature, and those can have much higher Q than resonators made out of room temperature components. And finally, there's things you can do like for long distance interconnects on chip. If in a hybrid technology, if you made the long distance interconnects superconducting, that actually improves the energy efficiency in adiabatic circuits. Whereas, it might be surprising, but it doesn't really help you much in conventional circuits, right? Because those are dominated by CV squared losses. And notice CV squared is not affected by the resistance of the charging path, right? So, so you get sort of this combination of benefits from adiabatic logic to cryogenic temperatures and superconducting interconnects that you couldn't get that through any other combination. And I mentioned high Q resonators already. All right. So that's it. So, I presented S2LAO, which is the first of what I call the perfectly adiabatic logic styles. And it's since been improved by Eric de Benedictus's Q2LAO. And Q there means quiet because he's kind of interested in these security applications for resistance to differential power analysis and other kinds of side channel attacks. And we believe that in principle that perfectly adiabatic logics should be capable of outperforming energy efficiency of any other known superconductor-based form of digital logic. And to actually realize this will probably require going to low temperatures, making ultra-low gate leakage devices. So it might require new process engineering to actually realize this. But there's no reason in principle why we can't get the energy dissipation per logic operation literally as low as we want as we, if we push farther into the cryogenic regime or and improve the device structures to minimize leakage. If the application can tolerate the lower frequencies that you have in the adiabatic circuits. So again, I think this may have some practical applications in the not too distant future for cryogenic applications. And it kind of underscores the point that, CMOS is not out of room if we consider reversible computing, that, we can vastly improve energy efficiency, without having to worry about continued device scaling, which is starting to become infeasible for CMOS. But it really requires paying careful attention to reversible computing, fully adiabatic operation, and attending to that design style and those design rules carefully. And this figure is just some inspiration I got from a friend who showed me this, and I was like 8 circles, and that kind of led me to thinking about an 8-tick clock cycle, and that's when I invented S2LAO. Okay, and so that's it. sorry if I went over.
I think let's thank Dr. Frank. So if anyone of from the audience have any questions, it's a opportunity to ask any questions. Anyone from the audience?
Yeah, I have a couple of things actually.
Okay, sure.
So, well, first let me say, yeah, I've been dabbling around with the reversible computing for a while now. And
Okay.
for example, 2 years ago, I had the undergraduate computer architecture course. I had all of the student projects building a little thing that we called AXA, which was a reversible instruction set machine with
Nice.
transactional memory support. So it was
Cool.
using reversibility for transactional memory. However, my big background is actually that I'm kind of an optimizing parallelizing compiler guy, although I guess I'm kind of better known as the guy who built the world's first Linux PC cluster back in '94.
Oh, cool. Yeah, yeah.
At any rate, with the compiler optimization stuff, I've been trying to reduce power because I've kind of had this horrible realization that I'm personally responsible for more greenhouse gas emissions than anybody I know. And so, yay for Linux clusters, right?
Yeah.
So basically, here's the point.
Right.
I have actually been able to reduce power consumption per computation by up to about 5 orders of magnitude
Wow.
by analyzing the code, not at the word level, but at the bit
Mhm.
level. So basically doing very aggressive gate level optimization.
I see.
Now,
Nice.
I've been targeting that largely to things like, for example, quantum computing and systems like
Mhm.
that. And I've actually got a kind of a version of quantum computing that isn't really quite quantum computing, but does represent entanglement and superposition.
Hmm.
But what it's really doing is it's using bit serial SIMD operations
Mhm.
that get used as basically chunks of regular grammars describing the pattern of different superposed values. Now, I'm
Interesting.
not explaining this very well because I'm trying to keep it short, but
Sure.
basically the question is, have you looked at doing any kinds of architectures like that that would be built out of conventional reversible logic,
Mhm.
but would have properties similar to what you see for quantum computers?
Yeah, I mean, I'm not familiar with that particular technique, but it sounds interesting. I mean, the conventional wisdom about quantum computing is that it gives you speed ups that are impossible to obtain classically. So, assuming that conventional wisdom is right, I would expect there's probably some scaling limitations to what you're talking about.
Well,
But
I cheat. So no. So here, let me give you the cheat. The cheat is, instead of trying to get the
yeah.
exponential reduction by using funny physics, I'm
Mm,
doing it by symbolic computation on regular grammars.
yeah. Well, I think if that actually works out, then you'll kind of revolutionize physics as well as computer science. I mean, that's kind of Nobel Prize worthy stuff if it works. So I hope it works out. I'd be interested to learn more about it. Maybe you can show me.
Yeah, well, what I'd like to do actually, I can send you some of the material on just kind of the overview of what this looks like.
Yeah.
And in particular, what I'd be most interested in finding out is there a reasonable way of using a truly adiabatic implementation of this to try and get the power consumptions down?
Oh, sure. Yeah. I mean, I would say for any classical computation, we can improve its energy efficiency by doing it adiabatically. And, there are overheads, obviously, from reversible
Right.
computing. So the advantages don't scale as quickly as you might think, right, if you ignored the overheads. But there are still advantages despite the overheads, right? So the overheads just sort of decrease the slope of improvement, right? But you can
Right.
still show asymptotic improvements. So maybe
Have
we
you
should
built
just
SIMD parallel machines before, or?
well, in a sense, the flat top chip, which was one of the chips I showed from the 90s, you could think of as SIMD. It had a 2D array of extremely simple processing elements, and those are each doing some fixed operation basically, but the data can encode a general purpose computation. So it was actually simulating a cellular automaton model. Which is kind of an extreme example of a SIMD processor, right? So you can think of it as, right? So, I don't think there's any reason in principle you can't do a SIMD array of reversible processing elements, but it's just it just would take some work to flesh out the details of an architecture like that. But certainly no reason in principle it can't be done. But I'd be interested in seeing your work, so maybe contact me offline and
Sure.
and
Thank
give
you
me
very
some
much.
links. All right, thanks.
Nice talk, by the way.
Oh,
Okay,
thank you.
great. So maybe one more question from the audience, and because of the lack of time, and then is there anybody, another student, anybody? Okay. So Mike, one question I have
Yeah.
for you actually is that when you look into some of these applications right now, so what do you think? Like I understand from the cryogenic perspective, do you think it could be useful for like biomedical application and all those things?
Um, that's a good question. I don't know a huge amount about biomedical applications. I mean, NMR machines require cryogenics just for the large electromagnets that they use, MRI machines, right? But I don't know if the electronics all needs to be cryogenic in those systems. I know very little about those applications, basically.
Yes. Another
Of
thing I
course,
was thinking maybe about the in-memory computing, like crossbar array type of ideas could be implemented, right? So, say example, like using them for
yeah,
deep learning application, something like that, right?
yeah. Well, I think you can do adiabatic crossbars in a way. My focus has been on digital systems, right? So you could do an adiabatic memory array, um, either a static RAM or a dynamic RAM, even if you get the leakage down low enough, so you don't have to refresh very often. Um, but it's kind of a lot of the crossbar stuff is analog, where they're trying to use analog crossbars to do a low precision matrix operation and things like that. And they're energy efficient from the perspective of you're maybe substituting for a bunch of floating point operations with one analog operation, but a lot of those schemes use memristors, and those are not, they're still dissipative, right? So because they're kind of resistors. So I don't know if those techniques can actually, they'll still have a thermodynamic limit, in other words, associated with them. But I think there is some room for exploration in the long term of more reversible types of analog computing. So you could have arrays of mem capacitors, for example, which are not as lossy, right? There'll still be some losses when you switch, when you change their weights, but they're not necessarily dissipative during operation, right? If they're a reactive element. And similarly, I think there's also opportunities for reversible analog dynamical systems. So I did a paper at ICRC 2016 that was on something I called chaotic logic, where you just have a conservative Hamiltonian dynamical system and you kind of just let it fluctuate, and you take advantage of the fact that the average values of these fluctuating variables will give you an answer that you're interested in. And so that's sort of reversibility at a different level. So the microscopic dynamics of the system is reversible, and you sort of adiabatically perturb it from one state to another. So that's another direction for maybe combining analog and reversible stuff. But it deserves more attention. I haven't spent a lot of time thinking about that because my main interest is in digital computing. But I think there's opportunities there.
So, so great. So let's thank the speaker. And I think this is the last colloquium talk from the
For
EC
spring.
department side. And so I think Dr. Johnson is here. He can, because it's the last talk from the EC colloquium for this semester. So Dr. Johnson.
Sure. Thanks, Mike. That was a great talk. Really appreciate
Oh, thank
it.
you.
And I'd like to thank everybody for coming to the talks this semester and in the fall as well. I thought we had a great series, and this one was no less, was outstanding. Hopefully everyone got something out of those. Good luck in the last couple of weeks of the semester as we finish up what is hopefully the last crazy COVID semester with weirdness. As everybody knows, we're back to what we hope is normal in the fall based on how it looks right now. And of course, that'll change probably in 5 minutes as soon as something else changes, but we'll keep in touch. Thanks, everybody. And thanks again to Mike for a great talk today.
Yeah, thanks for the invitation.
Yep. Thank
It
you.
was nice being there.
Okay.
All right.
All
Thanks,
right.
everybody. Yeah.
Bye.
Bye.
Thank you.
Bye, all.